Swayam Prabha. Digital India. Educated India.
So far we have discussed the various types of emitters which we can use, and what is the different characteristics under which type of layout they will be more suitable. Now let's go on to the next aspect of the drip irrigation system design, and for that we will like to see that how the emitter hydraulics work. What basically we are interested in is that what is the relationship between the emitter discharge, you can say emitter discharge, and the operating pressure. Because basically we are ultimately, our main interest is how uniform the application can be applied, the irrigation application, how uniform it can be applied, and that, since we know that is a function of the operating pressure, we also know that there are some losses which incur, as we have seen in the case of sprinkler irrigation system. So the drip and sprinkler irrigation system, the design aspects are almost similar. You have the similar situations. In the case of sprinkler irrigation system, you had the along the lateral you had the discharge, which was reducing discharge as you go downstream the lateral, a specific lateral. The same was true for the main line also. In this case also is the similar situation. The only difference is that the pressures, when you come to the lateral level, the pressures are much lower. The pressures are much lower in comparison to what the pressures were in the case of sprinkler irrigation system. So though the philosophy will remain same, but the relationships might change. That is what we are trying to look into when we go into the details of the design aspects. Which relationships are relevant now when we talk in terms of the drip or the trickle irrigation system. So, in other words, we can, as we know, most of us have gone through the basic hydraulics courses, and we have seen that the flow regime is a very important aspect, and you had introduced the Reynolds numbers to designate the flow regime. So in this case also we take the help of Reynolds numbers, and we evaluate the flow regime, because the flow regime will decide what is the order of magnitude of the prevailing pressures, and the flow regime can accordingly change, which in turn will change the characteristics of the flow, or in what we are interested, that what will be the behavior of flow in terms of the pressure variations which will be caused because of the retardants which will be introduced in the flow due to the friction losses. So the flow regimes are laminar. This we have already gone through that. Depending on the Reynolds number, we'll define the Reynolds number once again. If this Reynolds number is less than 2000, the flow regime is known to be laminar. It will be a unstable flow regime if the Reynolds number is between 2000 and a value of 10,000, is partially turbulent and this range, this is instead of 10,000, this is 4,000, extremely sorry, and when it's 10,000, that limit will be the beginning of fully turbulent flow. So anything beyond 10,000 is a fully turbulent flow. As you know, the Reynolds number is expressed as Vd by nu, and because of the various dimensions which we are, or the units which we are using for different items, we'll put this constant of 1000 also. This is the Reynolds number, which is a number, and V is the flow velocity in meters per second. D is the ammeter diameter, in millimeters, and nu is the kinematic viscosity of water, and this is expressed in meters square per second. And normally the value of kinematic viscosity is taken as 1 into 10 power minus 6 meters cubes per second at 20 degrees centigrade. Now this Reynolds number, you might have seen the Moody diagram, which gives a relationship between the Reynolds number and the friction factor, because basically we are interested in the friction factor, at how this friction factor changes with respect to the regime of the flow, and that is our basic interest. That's why we want to know that what is the regime when you are having a particular system when it's operating. At the time of design also you will know that what will be the operation policy, how it will operate, what will be the pressures, which will be the prevailing pressures or operating pressures, and that will decide what will be the regime of the flow, and accordingly you will use the appropriate relationships. Now it is from the Moody diagram, you must have seen that the friction factor F, that is the friction factor, is a linear variation, is a linear function of Reynolds number in the case of laminar flow. It will be a non-linear function of Reynolds number when the flow is partially turbulent or is also called the transition zone. And the friction factor F will be constant when you have the fully turbulent but in general you will find that the flow is very unstable in this zone when it is partially turbulent. In most of the field conditions you won't be able to have such a flow available for a longer period. It will be either laminar or it will be turbulent flow. So as far as the relationships are concerned, you will be either using the relationships depending on what is the prevalent flow at that time. If it is laminar, you will be using those relationships which are relevant to the laminar flow, otherwise you will use the turbulent flow relationships. Now let us see some of the possible relationships which might be put to use when you go in for the designs, and some of the possibilities are, because if you look back and see that we have gone through many of the individual emitters, so it will be a function of emitter, what type of flow will be prevalent along with the pressures and other things. So looking at the type of emitter along with the type of flow, that is what is required. So we might not be going through all the possible combinations. We will give you some of the possible type of emitters which are discussed here. Let us say the orifice emitter and fully turbulent flow. So if you have this emitter and the flow is fully turbulent, then the emitter discharge, that is what we are interested in. If I designate the emitter discharge as small q, this is equal to 3.6 to A into C naught to where emitter discharge is in liters per second, and A is the emitter cross-sectional flow area, as in millimeter square. C naught is the orifice coefficient, and a typical value of this coefficient is taken as 0.6 normally. G is the acceleration due to gravity, and H is the orifice operating pressure. And is expressed in meters. Let's take a case of if you have a long path emitter and the flow regime is laminar, then the emitter discharge Q is expressed as this given expression. Now, in this case, this term we have already, all the other terms are same, only F is introduced, which is the friction factor, and is a dimensionless quantity. Now, F, as you see, that is a laminar flow range. The flow regime is laminar. In this case, if you remember the Moody diagram, in the laminar range, the friction factor is expressed as 64 by the Reynolds number. So, that is what you have to see, that if your flow regime is known, then you have to use the F value, the friction factor value, accordingly. And in this case, the other term which we have not expressed so far is the L, which is the emitter length. In meters. Now, the emitter length is the long path emitter. The emitter length is not the physical length of the emitter, is the length of the path. The spiral grooves which we have provided inside the long length, the long path emitter. What is the length of that? Because that is the effective length through which the water is passing. And that is what has to be used in the case of a long path emitter. So, that will be given when you are given that this is a long path emitter, the length of the groove will also be given along with that. Let's take another case where you have used the same long path emitter, but now is in the turbulent flow. The regime has changed. The type of emitter is same, but the regime has changed to turbulent flow regime. In this case, the equation which will be used is also slightly different. This is h under root only, not including d. So this is the expression which has to be used for the turbulent flow case to find out the emitter discharge. In this case, the friction factor F is having a different relationship, and in this relationship the friction factor is given as this expression where this term eta is absolute roughness of pipe or the tubing in millimeters. Now is a function of the ratio of the diameter to the absolute roughness, because the friction factor will be dependent on what is the extent of the roughness of that material which is being used in the case of the turbulent flow. The only and this, while using this equation, you have to be careful that the units used for d and eta are the same units. They are not different units, because earlier we have expressed d in meters, and right now we are giving the eta is in millimeters. So when you are using this, both the unit should be same. That is very important for this relationship to be used. In literature, you will find that the value of the absolute roughness for different types of materials is available. These are the materials, or some of the materials which are normally used for the drip irrigation system network. For the plastic, the minimum and the maximum absolute roughness is given. So you will get an idea that what is the range to be used, or the value has to fall within this range while doing the design. The exact might change, because in this case also there is a lot of variation between the minimum and the maximum value. Then the commercial steel and wrought iron, there is the range. Galvanized iron is slightly higher, so this is in the ascending order. Aluminium is more than galvanized iron, then concrete, riveted steel, corrugated metal pipe. So all these are the suggestive values which can be used while doing the design. I would like to go through a small problem to give you an idea that how much these parameters can change when you go from one regime to another regime using the same type of emitters. In this case, in this problem, there is some data given. The given data is the design discharge is 4.0 liters per second, which is the requirement. The type of emitter to be used is long path emitter, and the operating pressure is 10 meters. You are using a micro tubing which has the inside dia of 1 millimeter. When we are discussing the long path emitter, I had not shown you, but I had just mentioned that you can, at an outlet, you can have the micro tubing instead. You can have 1 or 2 micro tubings for the water to leave the emitter. Now, in this particular case is the long path emitter, and the exit is through the micro tube, which has 1 millimeters of dia. And then the kinematic viscosity nu is taken as 1 into 10 to the power minus 6 meters square per second. Now, you are required to, what is required? You are required to compute the length of long path emitter. How much length is required if these are the design parameters, required design parameters to be fulfilled. That is design discharge of 4 liters per second with the operating pressure of this, and the other quantities are given. In this case, you can find out the velocity because Q is given, area is known. So, Q is 4 liters per I'm sorry, this is not 4 liters per second, this will become too much. This is 4 liters per hour. The design discharge is 4 liters per hour. As 4 liters per second is a very huge discharge, which is not required, specifically in the case of the drip irrigation. 4 liters per hour is the design discharge, and you have the area and this is 1.415 meters per second. Now, knowing the velocity, you can find out the Reynolds number, because now you have the velocity, you have the diameter, you have the new value into 1000. That is what is the expression which you have used. So, 1.415 meters per second into 1 millimeters by 1000 into 1 into 10 to the power minus 6 meters square per second. This works out to be 1.415, which is less than 2000. Therefore, the flow regime is laminar. So, you have a laminar regime. If your flow regime is laminar, you can find out the friction factor, which is 0.0452. Now, once you have the friction factor, then the emitter discharge can be obtained using the appropriate equation which we have just written earlier. This was the equation. which was to be used for the laminar flow for the long path emitter, and this everything else is known but for the L, and L works out to be 2.167 meter. All the other quantities are known, we already have their values, and L is 2.167 meters. Now, if we change one parameter, if we say that the required design discharge is not 4 liters per hour, but is 28 liters per hour. With this high design discharge, if you want to find out now what will be the change in length, you can find out the Reynolds number, and since the Reynolds number is a linear function of the velocity, which is again a function of the discharge, so you can directly find out the Reynolds number for this particular velocity, which will be prevalent at that time, for the discharge of 28 liters per hour, by using this proportionality. This will be 9,905, which is almost close to a value of 10,000. So, since is towards the fully turbulent side, because this it won't be in the unstable zone for a longer period. So you can assume this to be fully turbulent case. That means to get a design discharge of 28 liters per second, your flow regime will become a turbulent flow regime, and now the friction factor will be computed by this expression, and in this particular case the material which is taken for that, the value of the absolute the value of the eta, which we have found out in this particular case, I think from the table, the absolute roughness is given as 0.003, which is the minimum absolute reference for the case of the plastic. So, taking eta as 0.003, all the other quantities are known. The F value works out to be 0.0261, and now using the relevant equation for the emitter discharge, you can find out since the emitter discharge is known, which is 28 liters per hour. So you can substitute all the other values. The only unknown is the length, which will work out to be 0.024 meters. Look at the drastic variation in terms of the length requirement. The moment your flow regime has changed, and that is what we were saying, that in this particular case, when you talk in terms of the selection of proper emitters, it is very important to know that what will be the possible range which it can cater to, and you will also have to see that what is the maximum design discharge which is required, what is the minimum design discharge which is required, whether you will have a situation where you can cater to cope up with the total requirement throughout the season of the crop. In some cases, if they are the orchards, then it is year after year. You don't the requirement will still change. The requirement will still change because of two things. One, the climatic changes, where you will have the seasonal variation. The other will be the change in terms of the size of the plant. The plant, when it is small, then you will have less amount of requirement. As it matures, the requirement will also reduce, but that will only be different in the first few years. Once it has stabilized, then it will be only the climatic changes which will bring about the change in the requirement, and that will decide how your design should be. The options can be, again, either you can change the number of individual points, the number of emitters, that can be one option, or you can change the operation policy. So that is where you have to decide which one is the better option, whether you will like to change the number of emitters, or you like to change the pressure, which will in turn change the discharge. But here, the only importance of this particular going through this specific exercise was to tell you that there can be a drastic change in the requirements of the emitter. Okay, let's now next go into another aspect which we have seen earlier for the sprinkler irrigation system, which is the uniformity, the case of uniformity. Everything which we are doing with the assumption that we will be in a position to have uniformity of application, uniformity of distribution of water. And we had seen earlier in the previous case that uniformity cannot be 100%. It has to be, we have to lose something. You have to lose some uniformity, the higher the coverage you want to have. So if your extent of the network is very large, then there are chances that the uniformity will be, you will be doing that at the expense of the uniformity. That is very important to understand, because that will decide on your layout. It will also decide that the pattern of your operation, because if you have a very big area, the layout is not the only factor which will decide what will be the uniformity. You might be having a layout, but if you are operating in segments, then you are reducing the extent of the network which is influencing all these variations. So that is very important aspect. When you go in for the design, you will have to take all those things into picture. Let's look at the emitter uniformity. As we have mentioned in the beginning of this topic, that the emitter system, or the trickle system, is basically is intended to have a very close relationship between the crop water requirement and what is being supplied in terms of the emitter discharge. Now, the emitter uniformity becomes more important because of this fact, because if the discharge which you are supplying is not taking care of the requirement, and since the requirement has to immediately match with the discharge, you don't have a very large interval which is available, because of the fact that you are not, at no time you are trying to replenish the total deficit which you have been doing in the case of earlier irrigation systems. There we were trying to make use of the storage available in the soil. That soil storage, we are trying to dump the water in that storage and then keep on using that water for a longer duration. The dumping is at a much, not at, let's put it this way, that the dumping is at a much quicker rate. So you are using the basic storage which is available in the soil by bringing the soil moisture to the field capacity level. Whereas in this particular case, you might not be doing that. You are keeping the deficit, some level of deficit still might be there. And in some cases, even if you have started with a low level of deficit, by providing the uniform rate of input, you are keeping that deficit at a lower level. If you wait for a longer period, the deficit might increase, which might in turn increase the stress in the crop. So that will have a detrimental effect. So in this case, since we are the rate at which you are supplying the moisture is very low, if your crop water requirement is not being satisfied, if there is a deficit which is being created continuously, then if you accumulate that deficit over some period, it might become so much that it will have some drastic, some ill effect on the crop system or the crop, that particular plant or even that row of crop. So the uniformity becomes more important from that angle. The uniformity in this case, we measure in terms of emission uniformity. There is only a name or a nomenclature given to the uniformity. If we call UE as the emission uniformity, this is expressed as 100 into, since is expressed in percentage, so 100, 1 minus 1.27 by N into CV, Q minimum divided by Q average. The various terms which are used here, this is the emission uniformity in percentage, and N is the number of emitters per plant. Let me tell you that this is the uniformity of discharge along a lateral. The emission uniformity which we are expressing through this is the uniformity of discharge along a lateral. So N will be the number of emitters per plant for the case of point source emitters, on a permanent crop. Or N can also be, well, there is one case, either N will be this if you have the point source emitters, if you have used the point source emitters on a permanent crop, or N will be case A, the spacing between plants divided by the unit length of lateral line used by the manufacturer to compute CV. CV is basically the coefficient of variation, and B is case B is 1. Now the N value in this particular case will be either of the two, whichever is greater. Of the above two cases, the cases A and B which we have given for a line source. On annual row crops. That is how you determine the N. It will be either of the two cases, whichever is the greater value. When you have the line source, if you have the point source, then it will be the number of emitters per plant. Now CV is the manufacturer's specified coefficient, is provided by the manufacturer, and is a coefficient of variation, of discharge, and that is normally when the manufacturer provides emitter, he gives the value of the coefficient of variation of discharge, and Q minimum as the minimum emitter discharge and liters per hour. Similarly, the Q maximum as the we are calling it Q average. Q average is the average or design discharge again in liters per hour. That means if you know the the various quantities. If you know what is the minimum discharge, which is prevalent in a particular setting, what is the Q average, you can find out how much is the uniformity, the emission uniformity, provided you also know what is the value of CV, and you know what is the type of setting or the type of system which you have adopted. That will decide what is the N value. The CV is available for various types of emitters which have been manufactured by the various manufacturers. Now, I would like to give you some values of CVs for some different types of emitters, and how they can be classified on the basis of the CV value. This recommendation is given by the American Society of Agriculture Engineers. Recommended emitter classification. Based on the value of CV. Yeah, this is while selecting a particular emitter, you can see that what type of emitter it is, whether it is good, and looking at the value of CV, whether it can be accepted or you shouldn't be accepting it. So the emitter type, the value of CV, and the classification which has been put into depending on the value of CV. Now, for point source emitters, if the value of CV is less than 0.05, can be termed as a good emitter. If it is between 0.05 and 0.1 is average, is marginal, and if it is more than 0.15 is unacceptable. So, if your coefficient of variation is quite excessive, shouldn't be using those emitters. Similarly, for line source emitters, if it is less than 0.01 is good. So, in comparison, the coefficient of variation will be higher in the case of line source, is unavoidable. You can have a better coefficient of variation in the case of point source. So, it is between 0.1 and 0.2 is average class, it belongs to average class, and greater than 0.2 is marginal, or can also term it as unacceptable. Similarly, there is another information or a table which is provided, which can also give you a reasonable level of information in terms of what is the emission uniformity which is achievable with respect to the different types of emitters and with respect to the various types of crop spacings. So, this is the design standards for the emission uniformity. Again, this recommendation is given by the American Society of Agriculture Engineers, and this table I think I'll stop here for a while before we discuss this table, and then we'll go into the extension of this topic.